Nice invitation. So today I'm going to talk about the alpha S determination from static QCD potential computed on the lattice. And this talk is based on a collaboration with Hiromusa Takaura he is now in Kyushu University. He is a postdoc. And Kaneko-san from JLQCD collaboration at KEC. And Yuki Sumino, who is a professor in Tohoku University. Okay, this is this list of the alpha S determination from various experiments or simulations. And here one can see that Lattice QCD has an advantage. And these are data from Lattice QCD determination. And the error bars are small. And these are based on the first principle of the QCD Lagrangian, based on the first principle. And the non-perturbative effects are automatically included in the computation, and further improvement can be expected in the future. So that this is nice. Lattice QCD has an advantage. And on the other hand, static QCD potential is a good quantity for QCD coupling measurement. Intuitively, this is clear because the QCD potential gives the interquark force, which measures the coupling between quark and anti-quark. And there, theoretical tools are available, namely the effective Fourier theory and OPE exist for these quantity. And cube leading order perturbative computation is known so that we can utilize all these tools. And the data is available from Lattice QCD simulation. So we want to do we want to extract alphas using the Lattice QCD data combined with perturbative QCD knowledge. We extract alphas by enlarging a matching region of the OPE and the Lattice QCD for static potential. Lattice QCD is powerful in a relatively larger distance compared to perturbative QCD. On the other hand, perturbative QCD is very accurate at short distance. And without this special trick, for our case, it was not possible to match two theory because we do not find any overlap region where the two methods are valid. So we need to enlarge matching region in this analysis. Okay, and probably the next speaker, Johannes, will talk about the matching in a shorter distance region where they could compute a Wilson loop in a very short distance. Okay. This is the contents of my talk. I will explain about the static QCD potential. The important issue here is that infrared Renormalon. Because the static potential contains infrared Renormalon, if we do not do anything for this infrared Renormalon, we cannot have a nice prediction for the static potential to match with the Lattice QCD data. So we subtract this infrared Renormalon from the potential where we define the Renormalon subtracted potential. And this potential is used in an OPE formula so that we can make a comparison with Lattice data. And then I will explain Lattice setup and the data. And finally, I will perform the matching between OPE and the Lattice data, where I first take a continuum limit and then determine the alphas. And finally, I will summarize. Okay. This is the QCD potential. Here is the formula, one formula. Static QCD potential in the left-hand side is QCD potential in full QCD. This has a perturbative part, which is denoted as a Vs. This is perturbative part. So this starts at the three-level order. This is 1 over R. And then perturbative corrections start with logarithm corrections here and here. Unfortunately, this perturbative series is divergent so that this doesn't give you any precise prediction for larger distance region. And this unwanted behavior need to be subtracted, which can be done by adding these 2 times Gauss mass effect delta M. This term is added to subtract the unwanted term from this perturbative part, right? And then after combining this mass correction and the static potential, perturbative static potential, there remains still the higher order Renormalon effect, which should be absorbed or should be cancelled against the non-perturbative matrix element here, delta energy ultra soft. And this is expressed as a matrix element of non-local operator. And this was invented by Antonio and the collaborators around 2000. So we use this formula. Okay. The lattice QCD simulates the Wilson loop. Wilson loop is defined by the expectation value of the certain link variable. And then going to large T limit, one can extract a static potential by fitting this formula with a lattice simulation, lattice result. Okay. So for perturbative part of the static QCD potential, we use this formula. We use RG improved static potential in the perturbative side. And the RG improvement is done in momentum space. Namely, we involved alpha B. B is the alpha B is a specific coupling which is defined by the static potential in this expression. And this has to be fully transformed back to the coordinate space after RG improvement. This contains the running effect. And alpha B at leading order is equal to the alpha strong. And then, A0 is the 1, actually. And the perturbative correction start here. A1 is the one loop correction, which is known for long. And A2 was computed by York-Schroeder and Peter, this one. And N-cube leading was computed in these groups. Here, for alpha S Q square, we use for loop RG running in our analysis here. So beta function at the for loop will be used in this formula to evaluate. Okay. Unfortunately, this RG improved potential itself is not well defined yet. It's because of the Renormalon. Renormalon is known to be an infrared effect of the QCD potential. So I'm focusing on the infrared part of this static potential, perturbative static potential. I restricted the momentum integration at the low energy region here, so that this contains the Renormalon effect. And this is ill-defined because this integration actually cannot be done at all, because if one plug in the perturbative series in this alpha B, one can compute each coefficient at each order, but this coefficient is proportional to n factorial. N is the number of the loop or number of the perturbative expansion. And therefore, at each order, one can get the number. But finally, when you sum up all the correction to higher order, then this is divergent series, which cannot be summed up. On the other hand, this introduces certain kind of ambiguity, how to define this summation. On the other hand, how to see this ambiguity is, there is a nice way to do this, because the Renormalon is the infrared effect, so that we can do a certain kind of power counting, assuming that the alpha B at Q equal certain lower scale is 1, because this is a strong coupling at the low energy. So that we take this Q as a lambda. Lambda is basically proportional to lambda QCD scale. Then alpha B is 1. And the momentum, this measure of the momentum integration behaves like a lambda cube. And here is a lambda square. So that the ambiguity is counted as a order lambda, which corresponds to a leading order Renormalon, which should be canceled against the pole mass Renormalon. Okay? And then we do a series expansion for this exponent. There, I can expand this one argument because we are focusing on the low energy region of this exponent Q. Then one can Taylor expand this one, and then there appears a certain higher order correction in R, and linear term R in R is absent here because of the rotational symmetry. This integration plus minus direction just canceled out, and then next leading order effect is the R square, which have a lambda cube correction. This is next leading order Renormalon hidden in static QCD potential and higher orders. So we need to subtract this effect from the static QCD potential. So we start from the potential where we introduce the infrared cutoff here. Q is larger than certain low energy scale here. Now this is infrared Renormalon free because we excluded the infrared region. And then by doing a certain kind of complex integral analysis, one can get these kind of results, which was obtained by Yuki. And here, this infrared Renormalon subtracted potential start with a Coulombic term, which contains logarithmic potential, but this starts with 1 over R, and then constant part, and then the term which is proportional to R and R squared, so on and so forth. Now, what was found was that, okay, here, having this infrared cutoff, this is not a physical parameter, so that we want to let this mu to 0, so that looking at this explicit expression for this C0, one can realize that this C0 becomes divergent when mu f equal to 0, and C2 is also divergent because this is related to Renormalon here and here. So that basically, if one set mu equal to 0, then this is the original integral, which is, as I said, which is ill-defined due to Renormalon. So this C0 and C2 cannot be computed when mu f is set to 0. This is ill-defined. On the other hand, what is found in this paper was that this leading order term, Coulombic term, actually doesn't have any mu f dependence. So this is well-defined quantity. And moreover, linear term in R, this C1 term, is mu f independent. So that these two terms in this expression, series expansion, are well-defined, gives a well-defined quantity. So we combine these two terms here in this way, Coulombic term plus this linear term, which can be computed in a perturbative QCD. And at n cube leading order, this C1 coefficient can be evaluated. This has an integral representation, and there we perform the numerical analysis so that the C1 is given by 1.8 times lambda squared, lambda ms bar squared for a 3-flavor QCD. And this Coulombic term, we have an integral representation, which is a bit complicated, so that I will not show. But these are the prediction from perturbative QCD, and these are Renormalon-free potential, which we will use in our matching to extract alpha S.
But doesn't that contradict with E? Because I mean, there is no gauge invariant condensate in dimension 2.
This is the perturbative part. Still, I will combine this result with the OPE.
No, but that contradicts OPE. OPE tells you that it should start with R squared. There couldn't be a linear term because there is no condensate.
Condensate, you mean the non-local gluon condensate, right?
Well, I don't know about non-local, but if perturbation theory works, then local condensate is sufficient.
Okay. This.
If you had really short distances, local condensate will work in E again. The lowest dimension will give you R squared.
So this is this term, right?
Yes.
Yes. This term will be incorporated. I'm explaining only this part. So let me look at the behavior of this Renormalon subtracted potential. We call this as a Renormalon-free potential because we subtracted the Renormalon-dependent, mu-f-dependent part. Coulombic term is this blue line. So that this is behaved as a 1 over R here. And linear term is this green one. And adding up these two, we get this black line, which defines Renormalon-free potential here. Okay. Here is several comments. And cube linear log running is used to get this potential. And these are free from Renormalons. And if one draws the picture using a conventional RG improvement, which does not take care of any Renormalon subtraction, then it happens that this potential, conventional RG improved potential falls off at in a long distance region, which is not good to do the matching with the lattice QCD. In our case, we see that this potential, this rise almost linearly here. Okay. So this is a good potential. Okay. This extends OP validity region in a larger distance so that we can make a matching with the lattice QCD data. Okay. Now I plug in this expression in the OP formula. This is a full static potential, and we had the mass term and the perturbative part and the ultra-soft effect, which is non-local condensate. And then we split the certain Renormalon dependent part from here to here, C0 and C2. And we combine this mass correction, Renormalon related mass correction, and C0. And these are Renormalon free. And we combine C2 with the ultra-soft correction, which is also Renormalon free. Okay? In this way, the OP formula is Renormalon free if one combines relevant quantity in this way. Okay? When we make a comparison with lattice data, because lattice computation is done numerically, and this is a this gives a dimensionless result, so that we make a conversion flow dimensionful potential by multiplying inverse of lambda, and this will be compared with lattice data here. Okay, about lattice simulation, this was a part which was done by Kaneko-san. He is a member of the JLQCD collaboration. And he provided us the lattice data with a 3 setup with this size. And lattice spacing is given here, A1, A2, A3. Okay. And then fermion was the 3 flavor fermion, 3 UD Coke and the Strange Coke were included in the simulation using a domain-well fermion formalism. And in this simulation, pion mass was evaluated as a 300 MeV, which is a bit higher than physical pion mass. I will discuss about this difference later on. And KO mass is about 500 MeV, which is close to the physical value here. The action used in this simulation is order A improved, so that the discretization error in this simulation should be order A squared.
What is the gauge action?
Pardon?
The gauge action. Semantic?
I think so. Okay. Data analysis was done in this way. Statistics was investigated in a jackknife method. Chi-square fitting and covariance matrix was treated in this analysis. And continuum limit was taken by fitting the 3 lattice setup with A square fit extrapolation. We did the extrapolation to A to 0 limit. And in second analysis, we took into account the 3-level we take care of 3-level discretization error. And systematic error was as much as possible, we investigated the sources of the systematic errors. Mass effect was investigated, finite A, higher order effect, ultra soft effect, matching range, and factorization scale. All these sources were discussed in our paper. Okay. Here we found that there can be a 2 ways to do this analysis to extract alpha S. first analysis called analysis 1. This is the first attempt for us. And first, we try to extrapolate lattice data to lattice spacing 0. And then we perform the matching with lattice data. And there we could check that the discretization error is really behaves like a square. So that this was checked. And we checked the OPE validity region where the difference between perturbative part, lattice, and the lattice part should be proportional to order R squared. This was checked. And then in this continuum limit extrapolation, in some sense, there this kind of a model like assumption to do interpolation for this continuum limit, so that we were not so happy about this, so that we found another way to do this. This is analysis 2. There, continuum limit and matching with OPE was done at once simultaneously by a global fit. So this is good because this is a first principle analysis without any assumption. And there we could took into account one loop improvement, yes, for discretization error. Okay. So, okay. This is how we take continuum limit. So, okay, we have two lattice data. One is called the direction 1. Direction 1 measures the static potential in the x direction. So that the quark and anti-quark charge are separated in the x direction. And direction 2 is one step in x direction and one step in a y direction. So it's like a zigzag this way. So we have a 3 lattice setup for 3 lattice spacing, and we have 2 directions here. And the lattice static potential does not give a value for the constant part, so we subtract the constant part, V-lat, minus lattice potential at certain scale R1, which is defined by this one. And this R1 is known in the lattice community very precisely, so that we use this R1. And extrapolation from causes lattice to final lattice was done, and then finally we could reach the continuum limit. Okay, this is the result. So to control the finite A and the finite volume effect, we perform we use the lattice data in this range, R greater than 2 times lattice spacing, smaller than half of the lattice volume. And this is the result of our continuum limit. And the blue one is the direction 1 data, and the red one is the direction 2 data. Now I put the perturbative result. This is the blue line. Okay, lattice data and lattice data minus this perturbative result is plotted by this red circle, and the red line represent fitting with R square. Okay, and if the OP is valid, then the difference between this perturbative part and the lattice part should be explained by this R square behavior. And we observe that within this range, namely the lambda times R smaller than 0.8, we can see that this difference can be fitted by this one, so that we check the validity range of the OPE. While in the conventional perturbative method, validity range is about 0.3. Okay, so we extended the validity region in this Renormalon free scheme. Okay, here we check the perturbative convergence of this V Renormalon free potential. This black is the lattice data in the continuum limit, and leading order prediction from perturbative QCD is red, and next leading order green, blue, and cube leading log is this purple one. And here the lambda QCD is obtained, and we can see the convergence of the lambda QCD, rapid convergence. Okay. Now I'm talking about alpha S determination using this continuum limit lattice data. Okay, we will make a comparison with OPE with the lattice data, and then lattice data was computed in okay, this is a dimensionless quantity. We need to convert this into lambda, okay, dimensionless quantity normalized by lambda. And then we can make a comparison, and there we have a fitting parameter A0, A2, and lambda ms bar in this. Then lambda ms bar, 3 flavor lambda, is extracted in this way, 350 MEV plus minus 15 from statistical fluctuation. And then we plug in this lambda into coupling, and then we run up to MZ scale, and this gives a final result for the alpha S. Alpha S at MZ is 0.116 plus minus statistical error, and the systematic error is this one. And there is several sources of the systematic error here in this table. Okay. Okay. I'm explaining analysis 2. In analysis 2, the continuum limit and matching is done simultaneously, namely that we define the continuum limit of lattice static potential by subtracting certain discretization error. Okay, this is the original lattice data, and this term subtract discretization error coming from tree-level potential. 1 over r is just a tree-level potential. 1 over r in a scale parenthesis is 1 over r computed from lattice action. So this difference gives a discretization error for the tree-level potential, and this term should be subtracted from lattice data. And there, of course, this just subtract the tree-level discretization error. There remains certain higher order discretization error which can be taken care of by this term, and then constant term is subtracted. Now this is the continuum limit lattice data, and we make a comparison with OPE in this formula. So, and then, okay, these are the kappa is a parameter to fit, and here is a F is a free parameter, and C0 is a also fitting parameter. Here we have a 16 fitting parameter, and fitting range was chosen in this way, in this range. Okay. And after all, this is the result. Black is the continuum lattice data obtained in this global fitting, and green line is about our OP predictions. Okay. Okay. This gives the lambda ms bar in this way. And again, we plug in this result into the running of alpha S, and the alpha S at MZ is given by this one. And there we investigated several sources of the systematic error. And the list, this is a list of systematic error in our analysis. Finite lattice spacing effect, and higher order effect, ultra soft, and mass effect from this UD Cook, and matching range, factorization scheme dependence, lattice spacing error, etc. were all evaluated. This shows the final summary plot. This is the alpha S from FLAC review report and the PDG. And in our analysis, we got the two values from analysis 1 and analysis 2. Analysis 1 has a larger error bit, and the central value is a bit different from analysis 2. Okay. Okay, this is the summary of my talk. We extracted QCD strong coupling constant from static QCD potential computed on the lattice. In analysis 1, we took a continuum limit, and then we performed the matching, and this gives the result here. Here, matching range was taken in this range. R is greater than 3 times lattice spacing, smaller than 0.8, normalized by lambda ms bar. Okay, and this is a value for the 3-flavor lambda and alpha s. In analysis 2, we perform the global fitting, which simultaneously perform the continuum limit and the matching. And this matching range was taken in this region. R is larger than lattice spacing and smaller than this one. And here, the important point is that in analysis 2, matching was done in a shorter range compared to the analysis 1, so that this gives the better result, which has a smaller error compared to the analysis 1. So we believe that this is superior, so that we prefer the analysis 2. And lambda ms bar is given by this value, and alpha s is this one. Okay, thanks for your attention.
Thank you very much for this very nice talk. I guess there are questions.
Hi, could you please go back to slide 11? You say something about one loop improvement that you're doing there. Right, one loop improvement taken into account. Could you be more specific what you mean by that?
Sorry, this was not one loop. This is two-level improvement, sorry.
Right, so if you go back to now I think slide 18 or something, where you have the fit formula for the global fit, sorry, it should be 16, where the global fit formula is, right.
Yeah.
Here you have the A² corrections
Here.
for lattice artifacts, and since it's going like 1 over R cubed, it should be most relevant at short distances. And in that case, you would expect after doing tree-level improvement that this should start at order alpha, right?
This one.
The FD.
FD?
The FD should sort of be order alpha and order alpha squared, et cetera, which should then be running with 1 over R as a scale.
Or the alpha discretization error should be taken care of by this term, right? Because this is tree-level.
But tree-level improvement should be order 1.
But this should contain the alpha s, right? Static potential is alpha s over R.
Yes, but I mean, it's not a running coupling in that case. It's a tree-level improvement.
So that we don't know the coupling precise value, so that this is the fitting parameter in your analysis.
Okay, so you assume that there is no coupling dependence for the improvement terms. Okay.
Any other question?
Did I understand it correctly that you're using for loop running for alpha S? Is that correct?
Pardon?
You're using for loop running for alpha S? Or?
I think you mentioned at the beginning that you use the for loop running.
Yes, for loop running, yes. 3 loop S3 with a for loop running.
Okay, is there any specific reason why you're not using 5 loop running?
Because this is already improved potential. So the tree-level potential for this, we use a 1 loop running.
Okay, so you're correlating the two. So the order you have for the potential and the running, you're correlating these two. Okay.
More questions?
Maybe it's more general question that might be to the audiences. Is there any accepted standard way of estimating the higher order effect? First, what did you do?
Higher order corrections. Okay, this is the good question and probably difficult to answer. So that what we did in our analysis was that highest order in this analysis the S3 term. So 3 loop. Let me go back. Okay, this is the highest term in perturbative correction. So, of course, we hope that the next order is suppressed compared to this one. But to be on the safe side, we buried this, we added certain effect which is same as this one with a plus minus sign. And we buried the sign and we saw certain kind of
I see. So add and subtract the known, the smallest
highest order,
term,
yes.
highest. I see. Is that a sufficiently conservative way of estimating the remaining uncertainty in general?
This is the million-dollar question.
Yes.
So just looking at this expression, I was wondering what happened to the ultrasoft term, right? So at order alpha s cube, you have an ultrasoft term which is of order alpha s cube log alpha. So where did it go?
Yes, so that the A3 contains certain correction which is related to ultrasoft, this non-local gluon condensate. There is a certain scale, factorization scale. So this can be a source of the systematic error, how we choose this scale, ultrasoft scale. And so that this was incorporated in the error estimate here. So this one and plus 1 and minus 0 mean that we buried ultrasoft scale here. And okay, this is in unit of 10 to minus 4 in alpha S determination. And the final assignment for the error, systematic error is plus minus 1 in the unit of 10 to minus 4.
Okay, thank you.
Any unclear? May I have a question myself? So did you check what happens in your fits if you do not remove the u equals 1 Renormalon and do not fit for an a times r squared constant?
If we do not include what?
So you remove two Renormalons, the leading and the subleading.
Yes.
And then you have a counterpart. One of them is a perturbative linear rising potential you don't have to fit for, but then you fit for a constant times r squared. So I'm saying that you could remove this constant and also the subleading Renormalon and repeat your fits and check how, because you are the only one to my knowledge that has ever done that. So I wonder how much that affects the final answer.
Okay, this is the result of the parameter fitting in this global fitting analysis. And you are talking about this A2, right? Mm-hmm. So that A2 is this value with this error, statistical error. Does this answer your question?
Well, it is not compatible with 0. I guess, but you didn't try removing it from the fit. That's what together with the norm. I mean, to assess how important it is, the subleading Renormalon.
Okay.
You could just not remove it and repeat fits or do plots, see the convergence. Just wonder how it is.
This we did not try, but because we don't know this A2, so that we incorporated certain logarithm correction into this A2 and then try to see what comes out. And this was, what's this? Oh, so this was investigated in our paper, but not showing here. But
okay, thank you. There are no more questions. Let's thank the speaker again.